So it turns out that if you know left end and right end, you can calculate trap end easily. It is exactly halfway between the left and right Riemann sums. So we just do left end plus right end over 2. So from the example in our demo, we calculated left 4 and right 4 for the integral from 1 to 3 of 3x squared dx. So to find trap 4, I'm just going to do left 4 plus right 4 over 2. Okay, and those values that I calculated in the demo were 20.25 and 32.25. Average those, and you get 26.25, which agrees with the value I got for trap 4 when I actually drew trapezoids. So we have a nice quick way of calculating trap 4 without drawing trapezoids and calculating their areas and adding them all up. All right, let's compare our answer to the exact value of the integral. So the integral from 1 to 3 of 3x squared dx. I take the antiderivative of 3x squared, which is x cubed, and evaluate from 1 to 3. So that's 3 cubed minus 1 cubed, which is 26. So the exact area is 26, and my estimate using trap 4 was 26.25. Not bad. So mid-n also uses rectangles, but it determines the height of the rectangle at the midpoint of each interval. So I'm going to calculate mid 4 here. I have to go from 1 to 3. So here's 1 to 3. Break it into 4 intervals. So each interval, the height of the rectangle that I build over that interval is going to be the height of f of x equals 3x squared at the midpoint of that interval. So I need to calculate these midpoints. So this is 1.25. This one halfway between 1.5 and 2 is 1.75. Halfway between 2 and 2.5 is 2.25. And halfway between 2.5 and 3 is 2.75. So over each pink interval, I'm going to find the height of the rectangle at the midpoint that I drew in blue. So my base is a half. From 1 to 1.5, I still am drawing that same width or height of the rectangle, but my height is going to go up to the function at the midpoint, and then I'm going to draw the cover of the rectangle at that height. And I'm going to do that for each interval. So my interval from 1.5 to 2, the height of the rectangle that I build over that interval is the height of the function at 1.75. And I just continue to do that on each interval. Okay, so now I'm just going to add up the areas of my 4 rectangles. So this is mid 4. Each rectangle has a base of a half. So I have 1/2 times the height of the rectangle, which for this first rectangle is 3 times 1.25 squared. I'm plugging the midpoint of the interval into the function value. Okay, my next rectangle, it has a base of a half and a height of 3 times 1.75 squared. Third rectangle, base of a half times the function value at 2.25, so 3 times 2.25 squared, plus a half times 3 times 2.75 squared. And this comes out to 25.875. That is the closest value we've gotten to the exact value of 26. So of our 4 approximations, left 4, right 4, trap 4, and mid 4, this value is the closest to the exact value of 26. So far, mid is best for this example. Okay, for some functions, you can easily tell if the approximation will be an over or an underestimate. So your choices in the blank lines are written below the line. And we're going to draw some pictures to help us answer these. So if f is increasing, so let's draw a picture of an increasing function f. So increasing. Left rectangles will look like this. Which means that when you take left n, it's always going to be an underestimate of the exact area under the curve. There are little bits that I'm leaving out. So left n is always going to be less than the exact value of the integral. And right n, right rectangles are going to look like this. Which means I'm creating an overestimate because those rectangles all have a little chunk that's above the curve. So right n is always greater than the exact value of the integral. All right, what about when f is decreasing? Maybe it looks different. So here's a decreasing function. When I do left rectangles, I get something that looks like this. And that is an overestimate, which means that left n is above the exact value of the integral. And right n, when I draw right rectangles, I get a picture that looks like this. So these pink rectangles are an underestimate of the curve. So I put right n over here. So less than the exact value of the integral. Okay, when f is concave up, I want to compare mid and trap. So I need to draw a new picture. I'm out of room. A new page here. F is concave up, and I'm comparing mid and trap. Okay, so here's a picture of a function that's concave up. So let's just do one big interval because this has to be true for no matter how many intervals I use. So if I could do a mid rectangle on this interval here, here to here. The midpoint is at about right here. So I go up to my function and I build a rectangle that has the height of the midpoint. So now I want to know, is this an overestimate or an underestimate? So this bit is above the curve. And then I've got this bit that's below the curve. And it looks like I have more blue stuff than green stuff. So I am, in sum, this is going to be the area of this rectangle is less than the area under the curve. Right? So the blue part is an underestimate, and it's greater than the overestimate part. So mid is going to be an underestimate. So mid is less than the exact value of the integral. All right, so I'm guessing that trap must be an overestimate. Let's take a quick look. So if I draw a picture of a concave up function and I do a trapezoid to estimate the area under the curve, that trapezoid is an overestimate. There's this extra bit of area that I'm counting in the trapezoid. So trap n is an overestimate when we're concave up. All right, when we're concave down, it's probably going to reverse, but let's just draw a picture just to check it out. Okay, a function that is concave down, maybe like that. So for mid, let's say I want to do this interval, find the midpoint. I'm going to go up to the function, draw a rectangle. And now I need to compare the part that is above the curve I've got this chunk that's above the curve, and then I have this chunk that's below the curve. So it looks like the above the curve chunk outweighs the under the curve chunk. So overall, this is an overestimate. So mid is an overestimate when we're concave down. So mid goes over here because it is greater than the exact value of the integral. And then trap is probably going to go on the other side, but let's just look at the picture. If I draw a trapezoid for a concave down function, connect these with a straight line, that is an underestimate for the integral. Okay, this green area is a little bit smaller than the area under the curve. So I go back here and I'm going to put trap n less than or equal to the exact value of the integral. So if I want to integrate from 1 to e of ln x dx, I have all these ways of estimating: mid, right, trap, and left, and I want to order them with the exact value. So I'll draw a quick sketch. Ln x looks like this. Crosses the x-axis at 1, and I want to integrate until e. So the exact value under the curve is this. Now, if I wanted to, so let's write that down here. Integral from 1 to e of ln x dx. Now, some of these estimates are going to be underestimates and some are going to be overestimates. So first, let's just decide which side they go on. So left, a left endpoint rectangle would be this interval, and the height is the height of the function, so it's just 0. So left n is a very large underestimate. So left n is definitely less than the area under the curve because it's 0 in this case for one rectangle. Okay, well, let's see, what about right n? If I do right n for this same interval, I'm going to go up to the height of the function and draw a rectangle. So that is a very large overestimate. So that definitely goes to the right here. It is larger than the value of the integral, much bigger. All right, let's do trap. So trap n is where I would connect the height of the function at each endpoint with a straight line. And so I have this pink triangle. And that is a little bit of an underestimate. It's an underestimate of the value under the curve. But it's a much better underestimate than left n. So trap goes here. And then I'm going to guess that mid goes on the other side, but let's just draw a picture of it. This is getting a little messy, but we'll do our best. So the interval from 1 to e, I'm going to go up to the height of the function at the midpoint and draw a rectangle. So my overestimate piece is over here, and my underestimate piece is over here. And it looks like I have more area above the curve than under the curve. So this is in general an overestimate, but it is a much better overestimate than the right n was. So this is going to be mid n. It's an overestimate, but it's better than right n. Okay, we've done pretty well approximating curvy integrands with straight things, rectangles and trapezoids. We could do even better if we approximate our integrands with parabolas. So using a parabola to approximate a definite integral is known as Simpson's rule. So for example, I have this curvy function f of x from the interval from a to b. I could do a left rectangle. Terrible estimate, right? I could do a right rectangle. It's pretty terrible. The area under that rectangle is not a very good estimate for the area under f. I could do a midpoint rectangle. That's better, but still not great. I could do a trapezoid. Connect this point to this point with a straight line. That's not great. So that's using straight things, right? But what I could do instead is find the point at A and the point at B and a point at the midpoint on F and find a parabola to fit those 3 points. It turns out that for 3 points, for any 3 points, there's exactly one parabola that goes through those 3 points. So this red line I've drawn here, this red parabola, is a pretty decent approximation for f of x. The area under the polynomial p is pretty close to the area under the function f. So the formula derived by doing areas under parabolas rather than under lines is given here, and it is pretty messy. This is kind of like, ugh, right? I don't really want to do that. So luckily, it turns out that if you know trap and mid, you can find Simpson's easily. It's a weighted average of mid and trap. 2 times mid plus trap over 3. So to find Simpson's for 4, we just do 2 times mid 4 plus trap 4, both of which we've already calculated today, over 3. So that comes out to 2 times 25.875, that was our mid, plus trap, which is 26.25, all over 3. That comes out to exactly 26, which was the exact value under our curve. So Simpson's actually gave us the exact value because it fit parabolas to a parabola. Okay, so now for some practice with our 5 rules. So I want to approximate the area under radical 2 minus x squared from 0 to 1 using 5 intervals, and I'm going to round to the nearest hundredth. And then we compute the error by subtracting our estimate from the exact value of the integral, which I've told you here, and take the absolute value of that. Okay, so for left 5, I've given you a diagram to help you set this up. I just need to add up the areas of these 5 rectangles. So left 5 is going to be, I'm going from 0 to 1, and I broke it into 5 rectangles, which means that each rectangle is 0.2, width of 0.2. So it's 0.4, this is 0.6, this is 0.8, and 1. So each rectangle has a base of 0.2, and then the height is the value of the function at the left endpoint. So this value, it's a little bit less than 1.5, but I can figure out exactly what it is by plugging 0 into the function, 2 minus x squared all under a square root. So 2 minus 0 squared radical. My next rectangle, it has a base of 0.2 and a height of radical 2 minus 0.2 squared plus 0.2, base of my third rectangle, times radical 2 minus 0.4 squared. Continue like this until you've done each rectangle. 0.2 times the square root of 2 minus 0.6 squared plus 0.2 times radical 2 minus 0.8 squared. That's 5. 1, 2, 3, 4, 5 rectangles. The last one has a height of 0.8, the function value of 0.8. So I type this all into a calculator, and I get an estimate of 1.32. Okay, for right 5, I have the same interval, which means that my width My widths are 0.2 again, or the bases of each of these rectangles are 0.2. So 0.2 times this first rectangle, its height is now the function value at 0.2. So that is the square root of 2 minus 0.2 squared. My next rectangle, its base is 0.2, its height is 2 minus 0.4 squared, plus 0.2 times the square root of 2 minus 0.6 squared. And then my fifth rectangle, it has a base of 0.2, and the height is the function value at 1. So radical 2 minus 1 squared, and this comes out to 1.24. Okay, so for trap, I could draw 5 trapezoids, but instead I am going to average left and right. So trap 5 is left 5 plus right 5 over 2. And I just calculated these two. Left 5 was 1.32. Right 5 is 1.24. Average them, and we should get about 1.28. Mid 5, there's no handy formula for. I have to actually calculate it out by drawing rectangles. So I have 5 rectangles. Each one has a base of 0.2 again. So I'm going to have 0.2. And then the height of this first rectangle, it's the height of the function halfway between the left endpoint and the right endpoint. So the left endpoint is 0, the right endpoint is 0.2. So that value there is x equals 0.1. So I need to know the height of the function at 0.1, so I plug 0.1 into the formula. 2 minus 0.1 squared. Next rectangle, its base is 0.2, and its height is radical 2 minus 0.3 squared, plus 0.2 times radical 2 minus 0.5 squared. And that's 4 rectangles. My last one right here, the midpoint between 0.8 and 1 is 0.9. That is how I determine the height of that rectangle. So I've got 0.2 times radical 2 minus 0.9 squared. And this should all come out to 1.29. Just type it all into a calculator. And once I have trap and mid, I can calculate Simpsons by doing 2 traps plus a mid over 3. So 2 times trap, which was 1.28, plus a mid, which is 1.29. Wait, 2 mids plus a trap, sorry. 2 mids plus a trap, I got it reversed. Okay, so 2 mids, 2 times 1.29 plus a trap, 1.28 over 3, and that should come out to about 1.285 for Simpsons. So just as a little FYI, when you ask the calculator to evaluate a definite integral using the function integration command, it uses something like Simpson's rule called Gauss-Conrad quadrature, and it's a bit more complicated, but it's even more efficient than Simpson's rule. Less error.